Hello and welcome to the webinar on defending against the HatMan malware and cyber attacks on industrial control systems. My name is Keao Caindec and I'm the VP of Marketing at Mocana. And today I'm joined by Joe Weiss, the Managing Director of Applied Control Solutions, and someone who I've had the pleasure of working with and who is steeped in industrial controls and cybersecurity. So, welcome. We will be making this presentation available for replay, and also at the end of it or during the presentation you can download an attachment that summarizes a lot of what we'll be going through. During the presentation we'll also have some polls, some questions for the audience that we'll provide, and we'd really like to get some of your feedback on that, and we'll give you the cue when we run those. So, just to introduce Joe, Joe is an industry expert on control systems and electronic security of control systems. He spent more than 14 years at EPRI, the Electric Power Research Institute, serves on numerous boards for industry cyber standards, and is a director on ISA Standards and Practices Board, doing a lot of work in some of the work groups on ISA 99, and works closely with the IEC. He's published 80+ papers, my goodness, on all sorts of things, and if you're like me, one of the first books you've ever purchased in this area is Protecting Industrial Control Systems from Electronic Threats. So welcome, Joe.
Thank you. I'm looking forward to this.
Terrific. So jumping into this, we've heard a lot recently from December when this hit the news about the HatMan malware, also known as Trisis and TRITON. Tell us about HatMan, Joe, what it is and what this thing called a safety instrumented system is.
Okay, thank you. I think this is the first important thing for people to understand what this is and also what it isn't. People talk about industrial control systems. Control systems are what optimizes a process. That's what you can change. A safety system is different. A safety system is there purely and only to protect the system and people. It does not do any optimization. So it is basically, in a sense, dead as a doornail until the system gets to an unsafe condition, and then its only job is to shut the process down. So it's not there to change anything or whatever. It's there to be able to monitor, and if the conditions reach a prescribed set point, its job is to shut everything down.
Interesting. And this impacted Schneider Electric's Triconix controllers. Tell us about about Triconix and that particular system.
Yeah, I'm going to mention just a couple of things about Triconix, but I also want to mention one other point. The first time that I'm aware of that safety systems were demonstrated to be vulnerable and were compromised was in 2008 with the Siemens system. This is not a first. Now, the interesting part about Triconix is what tri means. Triconix is a triple redundant system. In other words, there are 3 independent processors there. That's the reason for the word tri and Triconix. And one of the things that this is also pointed out is redundancy does not equal security. And it's taken quite a while to get people to understand there is a real difference. Effectively, what tripped everything up was the fact that these 3 independent processors need to be, coordinated very, very closely. And if not, what you had was a plant trip, which is, in a sense, exactly opposite of what the hackers wanted. The whole purpose for the hackers was not to trip the safety system. It was exactly opposite. The whole purpose was to prevent the safety system from operating.
Interesting. Interesting. Well, tell us about the HatMan malware in particular, and kind of what happened there, and some of the details of how they compromised that system.
Okay, I'm going to just be very cursory because Paul Forney and Alex Keaindec from Schneider did a webinar, and they went through in pretty gory detail what happened. So I'm not going to be here to try to repeat what they've said. I would basically encourage people to go see that. But what was, in a sense, the issues here, as well as what was different, one of the big issues was that the safety system was connected to the DMZ. So what that said was the safety system, instead of being isolated from everything else, wasn't. There were also some other issues, again, I won't go into, but the big thing, if you will, that was new, or the 0-day, was the remote access Trojan that was able to get into the safety controller. That was new. But the other thing that's interesting, again, it was a 0-day. And until effectively Schneider did all of the analysis, that wasn't seen or picked up by any of the security technologies. And that's a very important point, that there was security there, but the security didn't find this. I mean, if the plant didn't trip, it's not clear when this would have been found.
So this was brought to light in December, at least to us and most of us in the audience. How old was this system? I understand the system and some of the processes. This is not purely a Schneider issue, but the system was quite old.
Yeah, the system itself was about 16 years old.
Wow.
Now, you have to also add, that's essentially when it's installed. You need to go back 3 or 4 years before that in terms of the development process. Mm-hmm. So the issue is when you're talking about systems like these, they're old and they last a long, long time. Mm-hmm. The other point I wanted to make too is, though it's a little bit different than with Stuxnet. With Stuxnet, you know, that malware was operable both from a reconnaissance and a destruction perspective for well over a year before it was identified. This apparently occurred in August, and all of the disclosures were in December. Mm-hmm. So you've got a couple of things in play here.
Interesting. Okay. So let's talk about that. Let's talk about what was different here, because this seems awfully familiar. You know, we've heard this before. This isn't the first vulnerability we've seen. This isn't the first attack we've seen on safety systems. But what's really different here about how we should think about what went on and how we start to get our arms around this in the future?
Well, again, I'm going to go back and forth a little bit between Triconics and Stuxnet with mm-hmm. Siemens, because in both cases, these things were detected not because the security systems detected it, but because of other reasons. And these are systems that, again, I want to go back because this is really important, had security. Mm-hmm. Is it, quote unquote, enough security or adequate security? Especially when you talk about sophisticated attackers, obviously not. Mm-hmm. And, you know, again, the other point, deviating for just a minute, how many times has this discussion come up, not in the world of ICS, but in the world of IT, which you've got all kinds of security technologies. Mm-hmm. So in a funny sense, I ask, why are people surprised when this keeps happening, not just in ICS, but in IT?
Yep, it's a great question. You know, we talked a bit about the vulnerability, the system, and what the hackers did to modify the firmware, make changes that they tripped, but also important to discuss is how they were able to get to the system and the vector of attack, and in general, more the vectors of attack to compromise a vulnerability. Talk a little bit about how these attacks, how these actors are getting in the first place.
Again, I'm only going to give you a general answer, but what you will see often is it's going to come in through your HMI, often which is Windows. You also have another vector that's, in a funny sense, tied to the Windows HMI, which is the serial to Ethernet converters. Because that same thing happened, if you will, not only in the Ukraine with the cyber attacks there, this is also, in a sense, how the black energy malware got into our U.S. grids all the way back in 2014. And again, the serial to Ethernet converters are there to take what we call the level 0, level 1 devices, the sensors, actuators, etc., which are analog to start with. They convert them to Ethernet to be able to put them onto the network and off into the Windows HMI. So you've got a chain there that has weaknesses in a number of different places.
Sure.
And it should be evident, or hopefully evident, that what I'm talking about is if you take the words Triconics or ICS, in a sense I've also described IoT or IIoT, and in many cases IT. Sure.
Now, this is a pretty standard model, right, of any DCS, and we have ways of protecting against this. We have firewalls and network filtering in the network. We have some, threat detection or monitoring. We have air-gapped systems. We have ways of separating networks. What went wrong here, and why, shouldn't those things protect against this sort of thing?
Often, and remember, I'm using the word often. Number one, we're reactive, and number two, much of our defense is based on previous exploits. And so, in a sense, again, I'm going to go back to Stuxnet for a minute. The concept of changing, configuration databases within a controller was kind of known. I mean, it was presented at the Siemens International User Group. But until it actually happened, and it was exploited and bad things happened, if you remember all the way back then, 10 years ago or 8 years ago, people went, oh my, how could that possibly happen? Well, you were told. Right. Okay? So the issue is, on a lot of this, our defenses are built on what has happened, or from kind of an IT perspective, what we think can happen. Mm-hmm. And when, if you will, an adversary that's basically doing something that's off normal or hasn't been done, mm-hmm. often we don't have the technologies there to find it.
Sure. Now, in the industrial world, it's different than IT. It's different than an Equifax attack or attack on Sony or Yahoo, where a lot of private data is compromised. What's the impact? How do we think about the impact on industrial control systems? What do people care about there?
Okay. And by the way, this is going to be reinforced Thursday, this past Thursday, January 25th. I gave the keynote at the Texas A&M Instrumentation and Automation Symposium, and that was the control and safety engineers. That wasn't the security people. First and foremost in the ICS world, and ICS includes safety, okay? First and foremost is reliability and safety. All the way at the end is security or confidentiality. Having said that, it's really not possible to be reliable and safe if you're not secure. Conversely, it's not really important, I'm going to turn it around, it's not really important to be secure from a control system engineer's perspective. It's not that important to be secure if security doesn't have an impact on reliability or safety.
Right.
Okay? Now that's not to say for the people who worry about, if you will, formulas or, critical industry confidential data, but from a control system operation or safety operation, it's all about reliability and safety.
Right.
And security is an issue if and only if it can affect reliability or safety.
Great. So we've just launched a poll here. So below the webinar player, we've identified several concerns that you might have. So take the next minute to respond to that, and we will let you know the results of what your biggest concerns are with regard to cyber attacks and ICS cyber attacks in particular. Okay. Going into some of these defenses, we've talked about this before, and we've talked about why some of these network-based techniques might be ineffective or less effective. And in this case, while there were firewalls in place and a DMZ, maybe there wasn't everything that needed to be done, right? So what we're seeing is that we're seeing many of these more network-based solutions not being particularly effective. And we're seeing a number of other attacks, right? And this is not the first, certainly. Stuxnet kind of kicked the door down back in 2010, but last year we saw an extraordinary number of attacks that impacted operations and companies, from Crash Override to Brickerbot, Palmetto Fusion, Dragonfly 2, and HatMan, and ones before that. What are your thoughts on this year? Are we going to continue to see these across software and hardware? Where are we going to go this year, Joe?
I believe that there's two answers to your question. Because the first one is, are things going to continue to happen? The answer is yes. The second part is, do we really have the monitoring to detect it? Because when you look at that, graph, it doesn't show a lot of actual cases. So this is kind of going back to this concept of Cyber Pearl Harbor. Will there be one? Almost for sure, yes. Will we know it's cyber? That's where the big question comes in.
Right. Because
the bottom line is, you have critical systems that must run, that can't be, can't be really air-gapped and can't be fully secured.
Right.
So there is going to be some amount of residual vulnerability. There has to be for them to be able to operate. So the point being, will there continue to be, exploits or attacks?
Right. Sure.
Yes. There have been for a long time.
Sure.
It's just we haven't had the ability to really recognize a lot of this as being cyber.
Interesting. There's probably a lot going on where it really doesn't get out there, so there are probably more than we actually see on the outside. So we got a result from the poll. What is your biggest concern about the impact of ICS cyber attacks? Number one is production downtime. So 51% of you answered that. Number two is personnel safety. That's 31%, so it's back to that reliability and safety. And then coming in third and fourth, third is tied for third, is environmental impact and impact to brand. We talked about network isolation and how we can put that in place. I think we also have to acknowledge that while we can talk about network isolation, it doesn't always happen, right? Let's face it, we still have issues where even though it is a policy, there are systems that get put onto networks because it's easier or because multiple groups want access to them, so they're not truly isolated. And whether you like it or not, I think we have to plan for that, right? We have humans, and we have changes in the network, and we need really a way to defend against that.
There's one other point I wanted to bring up too, that gets lost every time this conversation happens, because normally this conversation is, yeah, you need access, da-da-da-da. But the other point is, a lot of our systems have built-in backdoors.
Okay.
They've been built in by the vendors for specific reasons.
Mm-hmm.
This is part of the reason why air gaps don't really exist. So when you start talking about, do we really want, real isolation and segmentation? Yes, we do. How practical and realistic is it is somewhat of a different story.
Interesting. Well, let's take a poll on that. We're going to start a poll. We just started a poll. It's how effective do you think existing technologies are at preventing ICS cyber attacks? So when you think about what we have today in terms of all of the typical things, the air gap networks, the more perimeter defenses, more the network defenses, and policies and procedures, these are what tend to get recommended within the ICS cyber security standards, frankly. How effective do you think they really are today? And while you're answering that, I'm going to go on to authentication. We also saw that, with stolen certificates even, oftentimes if you compromise a password or even a certificate, you can get into these systems, and that tends to cause a problem, right? And that allows someone to log into a controller or a sys system and really upgrade the firmware. Updating the firmware with malware disguised as a valid update is part of the problem here. So authentication didn't quite work, and also once you had access to the system, there was no multi-factor authentication. Something that we live now with every day on our typical smart devices, but that was not in the system. Granted, it was old. Okay, here's what the poll said in terms of your thoughts on the effectiveness of existing technologies. 53% of you say they're moderately effective, probably a reasonable case there. 28% said not effective, and 10% said effective, and 3% said either entirely ineffective or very effective. So moderately effective wins today. But again, moderately effective to not effective, that is 81% of the people think that what we have today is either not working or only working so-so. Not a great story. So what can we do about it, right? We've talked a lot about this since December in terms of what can be done. And certainly there could be improvements on the operator side, on best practices, et cetera. But what else can be done? So here are some thoughts on how to really improve and get ahead of this problem, right? If we believe that a lot of what we've been doing isn't working very well, this is what we think can be done to get ahead of it. One is we have to harden the boot process, right? These devices, eventually, if you load malware on a device, you have to reset that device. It has to boot up again, right? So what we need to do is actually harden the boot process to ensure that we're comparing what should be on that device and what is on that device now to ensure that we can stop a reboot from taking place. Number two, well, before going on to that, you know, there are ways to do that, right, of locking down using verified boot, various secure boot technologies to ensure that the first stage of the bootloader process and the second stage and even validation of the OS and kernel are all taking place. This technology exists for embedded systems. This should be done on the gateways, on the endpoint devices that can handle it. And that would prevent a lot of malware from actually setting. We also believe that to the extent that we can, we should be implementing strong credentials, ideally digital X509 certs, but strong credentials in general, even if manually implemented, and multi-factor authentication. This would prevent things like a single certificate from being compromised, actually compromising the whole system. This prevents one operator, a good actor, from making a mistake that impacts safety and reliability. If we have multi-factor authentication, and we're talking about, you know, it could be multiple users for the operator or device owner. It could be an authentication issued by the manufacturer of the device. And it could even be a digital cert of the service provider. Perhaps it's an outsourced service provider that's used, right? But the more we can use multi-factor authentication, the more we prevent a single compromise of a cert or a single human from taking down a system. And
can I mention?
Go ahead, yeah.
The reason what Keao is saying is so important is what he's talked about has actually happened a number of times, including shutting down very, very large facilities. So this isn't hypothetical.
And then, of course, you know, we've talked about this before, and certainly strong and secure key management and encryption of the data is important. We know about that, right? But what we often don't do is ensure that the device is also using strong encryption and key management to actually ensure that the device itself is trustworthy. Right, I'm going to say that again, to make sure that the device itself is trustworthy. We're talking about the endpoint device, the gateway, and how they communicate to the cloud.
I want to just add one thing to what Keao said, and to clarify. Normally, in an IT context, when you talk about that endpoint, you're talking about a router or, you know, maybe a cell phone or a tablet or something. In the ICS world, that end device is a sensor, an actuator, a drive. It's a piece of real equipment that today has no security or authentication.
That's crazy. I mean, it seems like we need to rethink that, right? We continue to focus on vulnerabilities and chasing 0 days, patching them, and responding and getting our customers to patch. But sometimes it feels like we're chasing the wrong thing.
Yeah. And just to clarify, ISA 99 has started a brand new working group devoted specifically to what are called the Purdue reference model level 0, level 1 devices. You know, the sensors, actuators, drives, analyzers. And what we're basically asking is a few things. Number one, are the existing standards addressing this? And I don't think they are. And then the next question is, in a sense, what do we do? And actually an adjunct is, the Purdue reference model was developed in the 90s, you know, when you had companies like, you know, the big manufacturing companies who wanted to connect their DCSs to the ERPs. And security was never part of that. So part of this working group is actually trying to define in 2018 terms what is level 0, level 1, and what should be done. And by the way, if people are interested in participating, please let me know.
Excellent. It's a great thing that's going on. So I would say the other thing that we really need to get our arms around is the update process, right? Because to compromise a device and compromise safety and reliability, you've got to break through the network first. You have to get access to the device. Once you're on there, you have to take action. Oftentimes that means changing the application, which is through a firmware update or some sort of injection. Today, sometimes that can happen on anything. If you plug in into a USB port or into a serial port on older equipment, or just through a terminal connection, right?
Or a handheld communicator.
Mm-hmm.
This is one of the issues that's really a big deal when you start talking about, sensors, actuators, and drives are using these handheld communicators.
Yep, absolutely. So what we propose is that we really need to secure the update process, right? And this can be done by, rather than just allowing something simple like a hash and sign process for an update, actually use the cryptographic PKCS envelopes, for example. But we can use a variety of means. So what that means is being able to cryptographically sign an image or a firmware update, a software update. And that means you can, if you have multi-factor authentication, that means you can sign that firmware update by multiple parties, ensure that it's correct. You can ensure that it can only be unwrapped by the target device. But you get down in, and you can send it in an encrypted form. But you get to the point where even if a hacker got physical or network access to a device, they wouldn't actually be able to change the application of the firmware, because they'd have to break through multiple layers of certificates and break through the encryption on that device. So again, it's not any one solution, but this is an important part of what we think needs to be done at the endpoint to enforce and ensure that those updates and firmware updates are secure, and to ensure that we move beyond what we have been doing, whether it's in the network or through processes and procedures. So I'm going to take another poll here, and I want to get a temperature check on what you believe can be done to improve defense against ICS cyber attacks. So again, it's below the player. Feel free to take the poll, and we'll get the answers out there for you. So just to summarize, right, we talked about the fact that a lot of what we need to do is around moving beyond what is in the what we're doing in the perimeter, to talk about ensuring that we really focus on these endpoints and gateways. We talked about how we can do that with securing the boot process and updates and using multi-factor authentication. And we talked about how we can ensure that both the data and the application, as well as the device, are trusted. So in summary, and we'll get to the Q&A here, we talked about the malware attack. We talked about the Tritonix device, and that it wasn't the first attack on a safety instrumented system. We talked about the ineffectiveness of certain defenses, and we talked about some ideas that we have about how to really implement a stronger security model and lifecycle system to protect these devices and ICS systems. So a bit on Mocana. We work with a number of different industrial OEMs, manufacturers, to build security into their devices. Actually, we work closely with Schneider. We're good partners, and they use our technology throughout their ICS, their industrial control offerings. Again, some of the systems are very old and out there, so we're relying on the operators to upgrade that. But we work with most of the large major OEMs, and we're on about 100 million devices. And what we're seeing is movement toward improving those endpoints and devices, moving out of what they have been doing. So let me open it up now to questions. And the voting. Let me tell you about what we found. So 43 of you believe that the way to improve 43%. Defenses, 43% rather, believe that hardening ICS endpoint devices and gateways is the best way to improve defenses, followed by improving cybersecurity processes and procedures. I think that's very realistic, right? We've got a lot of humans in the mix here. Third are expanding monitoring and threat detection. I think also important. Interestingly, 0% said limiting the or deploying appropriate firewall and network filtering, and or limiting human error. So really, that's a really interesting result. Again, let's go through and get some questions from the audience. So below the player, if you have a question for Joe here or me, if you could submit that by writing it into the questions below the player. So go ahead and submit that if you can. Okay, so we have a question here on going into the background on how this what triggered what triggered the awareness on of this malware attack. How did we find out about it?
The plant tripped. Until then, no, the plant tripped. And it turned out the operator of the plant then called in several organizations to help them figure out why the plant tripped.
Interesting.
But it took the plant tripping for anybody to know, because this wasn't, if you will, controlling anything that affected plant operations. It wasn't visible.
Let's see, I've got a question for you, Joe. So, you know, this is, we got lucky here, it seems like, with this not actually impacting safety or blowing up a plant, if you will. Can you give some other examples of kind of how other industrial examples or critical infrastructure examples of where things broke down and how they impacted operations?
Well, let me start with one point, and that is, often it is very difficult to tell the difference between malicious or unintentional. And if it can be done unintentionally, it still can be done maliciously. And I want to stay away from, obviously, Stuxnet. I think most people are aware of that. You can go all the way back to 2000 when you had the wastewater hack in Australia. That wasn't damage to a system. That was basically essentially releasing almost 1 million liters of sewage under the grounds of a Hyatt Regency. So when you start talking about environmental, very big. You know, one of the things that got me involved early on was the Bellingham, Washington Olympic pipeline rupture. This was a pipeline rupture that ended up killing 3 people, causing extensive environmental damage. I mean, it released 230,000 gallons of gasoline into a creek. And the creek caught fire. Not the Ashtabula River, but a creek, you know, in Washington State. And it turned out that it was, the reason I'm bringing this up, even though it's old, is the SCADA system went from a nominal 3 to 7 second scan rate to almost 400 seconds to totally unresponsive. So right before the break, they lost all view and control of the process. SCADA went dark. Now, do we think that that was malicious? No, but it doesn't matter. But the other point is, going back to the level 0, level 1, all of the sensors, the logic was if the SCADA went dark, all sensors were set to an average value. So this became the first case, and this is now affecting not just cybersecurity but safety. So all of the sensors were set to an average value, which meant not only did they lose all view and control of the process, they had a loss of safety. And so this is because this is a very big problem. We've had other incidents where sensors have led to loss of safety.
Yes.
And that's why this is important. I mean, here's Tritonix now in 2017, when the intent of the hackers was to cause loss of safety.
Right.
That's the heart of what
Sure.
the control system or the control/safety system world is most concerned about.
Great. So we have a question about how does Mocana protect the device, the integrity of the device, and the underlying hardware. So at a high level, Mocana provides software. Our software sits on the chips and boards that are manufactured that go into devices, and we provide security software for that. We also have what we call an abstraction layer that ensures that it's easy to integrate that security software that we provide to a specific chipset, to crypto accelerators on the board, to other hardware-based secure elements. So our software is a simple way to help manufacturers and operators of critical infrastructure to improve security on their devices. And what we see is sometimes these devices have little more than local password authentication. There's no crypto on there. In other cases, they're using open source crypto libraries that just need to be replaced. But we defend and protect everything from avionics and controllers on airplanes and aircraft to industrial control systems in a variety of sectors: energy, utilities, discrete process manufacturing, etc. So that's how we protect against that. We're running up against the end of time. So what I wanted to do was thank you, Joe. Thanks for joining us. And any parting words?
Number one, I wanted to thank Mocana for doing this because I think it's important to get the message out of what happened and some, if you will, realism and understanding of what it is we're talking about and the need for the additional protection, which really isn't there. So with that, I wanted to thank everybody who's on or will listen to this in the future, and Mocana for inviting me.
Thank you very much, Joe. And if any of you have any other questions or want to follow up with Mocana or with Joe, please go to our website, mocana.com. Just navigate to the Contact Us page, and we'll be sure to route that question to the right people. And with that, I just want to thank you all for joining us, and stay tuned for more webinars from us. And Joe, I look forward to doing this again, and thank you very much.
Thank you all.